So this afternoon, what I'm going to talk about is analyzing curve data in concept and then some examples. And then, you know, most recently, my kind of the thing I'm on is looking at data for ICH Q14, which is like kind of like QBD or Six Sigma for assay development. And so there's some new guidance documents out that talk about some complicated ideas. And so I'm going to talk about a bioassay example um, in this where we do curve fit and then DOE with that together. All right, analyzing curve data. So let's get started here. All right. So first of all, if you're lucky, you probably won't have to use nonlinear models, and here's why. Um, if depending on where you are on your response curve, um, if you are lucky, you're going to be in this kind of middle simple linear model range where as you increase whatever the input is to the system, there was a that the response flattens out at the top. And at the bottom, you're increasing your input, nothing's happening, and then something starts to happen. And so if you're experimenting in the top part of that, or if you're at the bottom part of that, you can use a quadratic model, just the response squared, to look at that. I'm sorry, the x squared to fit a quadratic to that system and model that. Um, Sometimes we're looking at the whole ball of wax though. So like linear models are what we talk about almost all the time because they just work in so many different scenarios. Now, here are some examples where linear models don't work. So in the top range, we have nonlinear functions. So we have something like an exponential fit or something like a four-parameter fit or a Gaussian fit. We're going to end up with uh, one of our parameters for the model will be an exponent to make that work. Okay, and so that's kind of our classic nonlinear models. There's a whole another set of linear models, that third tier, where there are models that fit different types of data, uh, decay models or Michaelis-Menten kinetics models, um, four-parameter models that where the beginning and the end don't look the same. Where you have a hook at the end, kind of like growth curves. Like these are another type of nonlinear systems where you can't linearize this data with a simple transform. And then the bottom row, this is the squirrely data, right? This is where there's a lot of wiggles or unusual things in the data, and this is where we might go to fit functional models to this data that are going to do this kind of like in a piecewise um, direction. All right. So where nonlinear models fit work well. This is places where we have mechanistic models that fit these, and it's um, you know we have functions that we've known for a while that here's how you fit this kind of data. I think I already said that. And here's our wiggly data. I'm just going to move ahead. So when we're working with data that's not linear, it's got some curvature to it. There are a couple different strategies. So first of all, I come out of a little bit of a biochemistry background, and so log-log plots and reciprocal plots are great ways to linearize data. So it's a transformation of the x or a transformation of the y to get a linear response. And so you might be asking, is there some easy way to get between to toggle between different transformations in JMP? When it turns out there is. So one way is to use new formula column. It's just a right click, and I think I'll show that a little bit later. And you can add all kinds of transformations right inside your data set. You can do it within a graph and have temporary columns. There's a lot of ways to just add transformations. You can go into fit y by x. This is kind of a little bit older way. And you can use fit special. And in fit special, you have different options for transformations. So it'll transform the axis of the graph, and that's in fit y by x. There's another one that I like because it's all just button clicking, and then you can do comparisons. And it's if you go into degradation, that's under quality. Well, I'll give you a list to get there, but it's this really quick way to toggle back and forth. And then another transformation strategy is box-Cox transformations. And this is like a weird thing. Like if you see this, you're going to be like, Byron, I have no idea that was there. And that's like, this is a weird one. So if you go into analyze fit model and you only add a Y, like no X's, no effects, just add that Y. You can go into the fit model report underneath the red triangle menu, there's an option for factor profiling, and you can do a box-Cox transformation. And so a box-Cox transformation will take the data in whatever set it is, and it'll try a whole series of transformations to give you the best fit in somewhere in between like the square root transformation and a log 10 transformation. So it tries a whole bunch of things and it tells you what that best um, parameter is. So it's not like natural log 10, square root. It's like, well, it could be like root 0.5, so weird stuff can be in there, but it does a nice job of transforming data. Okay, so a really straightforward curve fitting strategy is to go shopping for models. Okay, and usually this sounds like a bad idea, but in this case, it's a good idea. If you're taking notes, I've got this orange phrase written there. It's statistical details for the curve fit platform. And if you Google that, you're going to find a table or a list of model types and the kinds of data that they fit. And so you go shopping and you say, oh, hey, my data looks like this. I'm going to try and fit that model to it. And then we can just go over to fit model and try fitting models of that type to our data. So this approach is kind of actually it's my go-to when somebody sends me weird data. It's like, well, I think it looks like this one. Let's try that fit and fit curve and go from there. Okay, so for curve fitting strategies, first of all, double check your data. Some models can't have values that are equal to or less than 0. And that's kind of an important thing. So if you're going to log transform something and your first time point is 0, that's not going to transform so well for you. So you might need some really small decimal there in its place. The launch dialog for fit curve has changed. There's some new things. You can just use stacked data format like we always have done, but oftentimes I have data that might be in a different format where I might have to do some transformation of the data, like stacking and splitting before I start. These options let us get to where we want to go without having to mess with the data first, which is really handy. And then there's this supplementary Z variables. This is a place where you can put covariates and you can put VOE factors to look at the effect of things that are changing across different curves that you fit. Okay, so if you haven't looked at the fit curve platform in a long time, in JMP version 17, there were like 19 new models added to it. And I think there were like another 6 or 8 added in version 18. So it just keeps growing and growing. The capabilities are pretty fantastic. So, and also, if there's some model that you would really like to have, submit that, go to our community.jump.com page, community.jump.com. And at the top, there's a wish list, and submit a wish list like, hey, this function is really important for industry XYZ. It'd be really great if this function were in there. And then, if people upvote that, then that might get added in a new release. There's another option too. So we have nonlinear and fit curve. In nonlinear, you can add models and then work with those also. And that's a little bit complex to show, but it's in our documentation for how to do that. Okay. Functional models. So this is more of a JMP Pro feature, but anytime we have we have data that are functions like signals or series or really unusual patterns like chromatography data, we can fit those using the Functional Data Explorer. It might require some pre-processing of the data, like normalization or transformation or a whole bunch of other things, dynamic time warping. All of that can be done as pre-processing steps. And a really great feature of that whole platform is that you can use the bi variables to fit the same rule set to lots and lots of different groups of curves so that you can get more out of those. Oh, yeah, and I got to add this in there too. I know these aren't nonlinear fits, but there are other fits that are kind of important depending on your industry. Passing Bablock was added to the Fit Y by X platform, and it replaces an old add-in that was there. And the cool thing about passing Bablock, this is something where you're looking at equivalence between two measurement systems, or things where there's error in the X and error in the Y. Um, so once you fit passing Bablock, you can go right there to Bland-Altman analysis, which is kind of like a special version of matched pairs. Just pretty nice. Okay, so let's get jumpy. All right. So I mentioned this idea of an interactive data transformation. So if you go to the Analyze menu and you go to Reliability and Survival, and you look at degradation or destructive degradation, I'm just going to grab a data set here, and you run that. So that's like going File, Reliability, Survival, uh, Degradation, here it is. And you pick this first tab. I talk a lot about stability for pharmaceuticals. In that case, we're starting off over here, but this is starting over here. Okay. And what you can do, this first starts out, this is strength versus time. And now I have the ability to apply transformations just by button clicking. So I can say, well, what if I wanted to use a reciprocal plot, or a log transformation, or exponential, or I can go through these and try lots of different things. If you want to add a custom thing right out of a formula that's you can get out of the scripting index, you can do that too. And there's some examples in the scripting index of how to set that up. So once you find a transformation that you like, you can say generate a report for this. So I'm going to do that. And it's giving me this AICC, the Akey's information criteria corrected. And so we can compare different kinds of fits based on this AICC number, or BIC, whichever one is your favorite. But the idea is the lowest value is the best. So if I were to do a log and square root transformation of this data, that's really linear, and I run that just by clicking on that button. Now I have a comparison of those two model intercepts, and it tells me what they are. So you can just go through here and try lots of things, and then you look at this and you're like, hey, that's got a really low AICC. It's a big negative number. That's a better fit than other fits. So really handy model selection tool to use there. So let's talk a little bit about enzyme kinetics. Kinetics are something that I've always used other specialized software for enzyme kinetics, but being able to use JMP for this makes my life a lot easier. So in this case here, I'm looking at an example where I have my favorite enzyme in the whole world, prostaglandin synthase 2, and we're using two different inhibitors, Vioxx, one of the greatest drugs in the world, and meloxicam, not quite as good, but still pretty good. And these are inhibitors for these, and we can fit. Hang on a second. There we go. So we can start off and fit these first order decay curves to these graphs, and it's just coming over here to specialized modeling and fit curve. Okay, and then from fit curve, we can put in the time and the concentration, and then we're going to group this by inhibitor and say, okay, all right. And then we start off from there. All right, and then the fitting itself, I'm just going to go to the red triangle menu, and I'm going to come over here to rate equations, and we're going to do a first order. Okay, and now I've got fits of those first order curves, and I've got rates for each one of those curves also. which is handy. Okay, and if we were doing enzyme kinetics, we might use a um, similar workflow. And hello, oh my goodness, the there we go. So here we've got that Michaelis-Menten shaped curve, and again, it's just go to the menu. We're going to go to rate equations, fit Michaelis-Menten, and then what we get are the Vmax um, and Km for each of these curves, which is handy. And then also, if you're going to do something else with this, you can just right click and say make into a data table and pop that out and use the data from there. So in both these cases, the data format here is in a tall format. So I have one column per variable, one observation per row. That's the same over here for this one. Okay. So let's look at some other examples. Oftentimes somebody will ask, hey, how can I practice doing different curves? There's a Antonio Boschi's web page on kinetic mechanisms. He has a bunch of data that you can download and try fitting different kinds of models. And that's, good Friday afternoon fun if you are jumpy. Okay. Another type of curve that we can fit with jump, and this is kind of something a little bit more specialized. This is dissolution curves. So um, for everybody in pharma world who is making tablets, we're usually worried about, is dissolution staying the same with our tablets? And so we have to do some comparison of dissolution times, and our data for these will look something like this, where we have these dissolution curves, and I'll have some reference, the one that's in black here, and then I'll have a different test articles, from different other batches that I want to compare back to the reference to show or to ask the question, is dissolution the same for these? And we could fit models to this, and this is where we're kind of changing the rules. Instead of fitting like a mechanistic model or a function model to this, we're going to use a Bootstrap approach. And so here we've got that data loaded in fit curve. We have our reference and the other test articles here. And then from here, we're doing this, it's called F2 analysis. And then we can compare test to A, test to B, test to C. Okay. And it's giving us the conclusions of those. Also, it's keeping track of how many points are above the 85% dissolution level, and it won't use those like it's supposed to. So this is a really useful platform. All right. So I've mentioned some things about functional data explorer in JMP Pro, and I just want to show an example of that really quickly. In this case here, I have a whole bunch of growth curves, and they're kind of overlaid here, so it's hard to see them all together. But there's a bunch of them, and this is that catalog of growth curves. And so these curves come out of a manufacturing process. So this is kind of like ad hoc data where some things are different across these, and we're looking at temperature during the run being a little bit different, and pH being a little bit different across the range. Okay. And so the cool thing with this is we can say, well, what's the effect of running this at different temperatures? And we can see here that the curve flattens out, and we get to that peak, and that peak gets a little bit higher later if we're using a higher temperature versus a lower temperature. So our growth rate is changing, but we're able to see that in the shape of the curve. And then the pH, we can see that death curve at the end where lysis starts to happen and the cells start to break apart. We can see that if we want more lysis to happen, we can use a lower pH, or if we want things to be a little bit more stable, we can use that higher pH and maybe a lower temperature. All right. So kind of moving in that direction, we've into the direction towards the clinic. Something that a lot of people do are pharmacokinetic assays. And so what I'm going to do here is just a quick visual of what that would look like. So I've got different subjects. They've got different dosing strategies. I've got the weight of the subject because the bigger you are, the harder you fall is kind of the idea. So somebody small with the same dose that's going to go into their system faster and come out faster than someone who's larger like me. So if you give Gail, this dose of 2, her serum concentrations or her excretion rate of the drug will be really different than mine. So I'm going to fit that with the fit curve platform. And this is an example. Let me come back over here, launch the analysis. Okay, in this case here, I'm putting dose and weight down here, and I'm going to fit this for every subject. So this is that Z supplementary variable for dose and weight. Okay, and then once I fit, this is a 1-compartment oral dose. Then I can come down here and say, okay, this is the dose response curve. And, as I've had lighter people, that dose response curve changes. And I can see that across the range. So, my excretion rate is going to be really, or my area under the curve is going to be different than Gail's, and that's a weight dependent thing. Okay. So that's an example of what that supplementary variable can be used for. So something I see a lot is that people are using DOEs and fit curve together, and there's this really big confusion over like what goes into the DOE. Okay, and a lot of times in the biologic side, we're doing things that are bioassays, and that means that we take cells and we do something to them and we watch to see how they respond. And a lot of times there's a dilution associated with that. So, for example, if we were using a 96 well plate, this is just using 8 columns and all 8 rows. We would have the same dilution across all the plates of the inhibitor or whatever it is we're looking at, and then each row would be, or I'm sorry, each of these columns would be a different treatment option for this. And one of the things that's kind of neat about working in these 96 well microtiter plates is that experiments are super, super cheap. And so they can do lots and lots of experiments all at the same time. So in this case here, we're looking at a bunch of parameters that have to do with the XA execution and the cell preparation that goes into these plates. So we can look at a lot of things. And as a result, we end up with these really gigantic experiments. Okay. And in these experiments, sometimes there are things that we need to keep together. Like, for example, in this experiment, I've got a CO2 concentration in the oven that we're putting the cells into and a temperature. And I can't have some of the plates in the oven at a different temperature because it doesn't work because it's just one oven temperature. And then also, we've got different CO2 concentrations, and the CO2 concentration is the same in the whole oven. It's kind of a pain to get that dialed in. And so you want to hold those things together as you do those experiments. And it comes into this idea of blocking in DOE. And so in this example here, I told Jump, hey, I want 64 runs because 8 times 8. And then each plate is going to have 8 of those columns. And I want you to block on those 8 columns. And I want you to keep CO2 and incubator temperature together and vary those separately. And so then we end up with experiments like this, where each one of these is a plate. My blocks are my plates for this. But looking at this, there's a pile of samples. So what we have to do in the assay is we need to take each of these rows here, or each of these columns, and analyze each one of these separately. Okay. And so that data ends up looking like, so our data is going to be in this format. Okay. And people who have heard me talk before, I always talk about 1 variable per column, 1 observation per row. Well, in this case here, I've got each run as its separate column. And we could go into this and say tables stack and stack up all the runs and then do the analysis. But in the fit model platform, this kind of gets streamlined because we can say, oh, I've got this is my regressor, and I've got every column is its own thing. So I could say, here's my regressor, and here's all of my columns, and I can just put those in here, and then we'll fit all of those together. Okay. So it just simplifies kind of our data steps to get things going. So then in this case here, we would look at each one of these curves and we would fit like a 4-parameter logistic regression to each one of those. And then there's this great function underneath the red triangle menu when you're using curve fit. There's this make parameter table. And when you click that, then you get the parameters. So this is that upper asymptote, the lower asymptote, the growth rate, and then the middle is the inflection point, your IC50 or EC50, depending on which way your curves are going. All of those things put together along with errors. And now these things here become the responses to the DOE. So I've got in my DOE table, let's see if I've got that here, I hope. Like I said, I made this as complicated as I possibly could. So in my DOE table, I have all of those things together. Yeah. So now I have that upper asymptote, lower asymptote, growth rate, inflection point. So and you can see I'm not doing anything with the dilution. So don't come over into the assay. Everything stays here where we're just looking at our different responses for this experiment. So just a couple things on like how to set up and analyze bioassays with nonlinear and DOE together. This concept came up like probably in 8 different conversations last week.